Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, we would like to tell you all that in our previous session we talked on wireless multimedia networking. Dear friends, we would be continuing from the point where we left and we would be discussing more on wireless multimedia networking. This is the part 2 and we would like to tell you all that for this very discussion on wireless multimedia networking, we have once again with us in our studios Dr. Advitya Sinha. Dr. Advitya Sinha is Assistant Professor in Department of Computer Sciences in one of the leading institutions. We hope that her experience would definitely help us out in understanding and knowing the topic in detail. Hello ma'am, welcome to the UGC lecture.
Thank you. Hello viewers. This lecture is a continuation to the last lecture that we were continuing on multimedia networking over wireless domain. So what we have already discussed about is the significant applications and challenges associated with it, different characteristics of multimedia networking. We also spoke about the cellular architecture that forms a standard basis for communicating the multimedia supported content and services. Also, what we came across was a phenomena called handoff. So in this lecture, we'll address the remaining topics, the handoff initiation. That is, in the last lecture we went through what is the importance of handoff, what handoff actually is, then it's if once it is detected, then how it has to be managed, the resource allocation and deallocation, how it has to be managed and who it is being managing by. Maybe the network administration is managing, that calls for a centralized approach, or it can be a decentralized approach or semi-decentralized approach by the mobile devices. Okay, so in this lecture we are interested to know about what initiates handoff in the first place. This is followed by the quality of service parameters, mainly exploited at the connection level and application level. Then we'll speak about the channel capacity improvement, that is the different improvement techniques that are used by the network administrators as a tool for adding and supporting more and more number of users in a particular cellular region. So these are the important techniques that are associated with it. Then we'll discuss about the traffic and energy related issues later. Now, handoff initiation. Now what happens, there are different cases for this type of approaching this type of problems. So going with the first one is relative signal strength, or RSS for short. In this method, the decision that is used for deciding whether a handoff should take place or not, this decision is taken up by the mobile device and it is purely based on the mean measurement of the RSS of adjacent base stations. Okay. And once the mobile node collects the signal strength, that is the relative signal strength of the neighborhood base stations, or the base stations lying in the close proximity, then what it does, it puts a check on among all those base stations whose relative signal strength is relatively stronger, and the base station from which the mobile device is getting higher level of signal strength, it will decide to switch over to get its services switched over to that particular base station's coverage. It's a very simple technique, and because of its simplicity, it can be easily widely used and implemented in the multimedia devices. But what happens, there are very important limitations associated with this very basic the technique. The first and foremost is it triggers unnecessary handoff. Now why unnecessary handoff? What do you understand by unnecessary handoffs? So let's understand it with the help of this diagram. We can see that there are two towers, the blue and the green towers. Say the blue one is our first base station designated as BS1, and the green arrow shows the second base station, BS2. And the trend the blue trend, it shows the diminishing rate of, there is a fall in the level of relative strength as the distance increases, and similarly we have the decreasing trend of the base station 2. Now there is a mobile device that supports multimedia capabilities. It's in its movement, and whenever it passes the junction of both the base station's relative strength at point A, it hits and it triggers a handoff. Now when it triggers a handoff at the position A, what happens? There is a network time and resources that are engaged in this particular activity of handoff process is wasted. Why wasted? It's because that whenever as the nature of the transceiver is concerned, the transceiver's coverage is actually a circular coverage. It resembles a circle somehow, right? Now what happens when the any vehicle, any moving object, any multimedia handheld devices tend to move out from the core of the transceiver to the circumference, then at the circumference the level of the RSS tends to fluctuate, not at a particular point, because RSS is not strictly a rigid value. It tends to be within some range, okay? And very importantly, when it goes to the boundary, the circumference of the circular coverage area, it tends to fluctuate more between those allowable ranges of values, okay? And when it starts fluctuating, it becomes very difficult for the mobile device to decide whether it should belong to the coverage of the existing base station or it should switch its services to the next base station. And this decision is very instantaneous, because since it's the RSS of both the mobile base stations are fluctuating, which means that instantaneously the decision taken by the mobile device may fluctuate between whether it should be in the coverage of BS1 or BS2. And this can go on for quite a long distance, because here we have shown that it's a point A, but rather than a point, it can be even a location, even a position that spans over quite a few meters or even kilometers, okay? So during this time, along this area, what happens? The device remains in a very ambiguous situation as to which services, whose base station services should be taken, and this creates a type of effect known as ping pong effect, okay? So ping pong effect is it's a repeated handoff. It results as a repeated handoff due to rapid fluctuations at RSS, more importantly at the junction of the two relative strengths of the relative base stations, okay? And whenever there is a handoff, you know that network time and resources are engaged. Time, because it takes quite a long duration to switch over the resources of the existing to the next potential one, and this is a very crucial time that the network administration has to patch up between the services that it is being currently providing a particular user. So wastage of network time and resource are both very important and is highly to be concerned of. So due to all these problems that we have with RSS scheme, we switch over to RSS with threshold. Now in this method, there is one more parameter, added parameter, as you can see that it's a threshold parameter. The threshold is a function that takes input the relative signal strengths of the mobile terminal itself and the base stations. Here we have taken two base stations into account, but there can be any more number of base stations depending upon how many number of adjacent base stations are there, okay? Now say for example, the threshold is being calculated and it comes out to be some Ti, okay? Now Ti is obviously a particular value, unlike the RSS, because RSS is not a rigid value, but this threshold will be a rigid value, okay? Now, whenever this threshold is violated, whenever a mobile device experiences lower strength of relative signal from a particular base station, and this level falls beyond a threshold, say Ti, then it triggers handoff. It decides to hand off from the services of the existing to the next adjacent base stations. Okay. So, as given in the diagram, if we see that if we have taken T1 as our threshold, it will behave exactly the same as our RSS method alone used to do. Okay. So, taking T1 as a threshold, it will not perform any better than the RS method. So, let us suppose we have taken a lower threshold, that is lower below T1. What happens in this case? The handoff activity will get delay more into more farther distance, and it will occur at location B. So, what we are doing here, we are basically trying to delay the handoff process as far as possible, but keeping in the mind that the quality of service should not get disturbed. And how this quality of service will get disturbed? If the relative signal strength falls quite low, that is even lower than what the mobile device can actually it can take. So, it is known as the tolerable level of RSS of that particular device. Sure, it should not fall beyond the tolerable level of the mobile device. Now, what are the some limitations that are associated with this method as well are the calculation of threshold. It is very important, because if we inefficiently calculate the threshold, it would lead to reduction in the link quality. That is, there can be, as we have seen in the earlier method, there can be some kind of, say, ping pong effect, or there can be other technical glitches which will hinder the users to acquire the multimedia services, other networking services in a proper manner. And obviously there will be dropped calls, disconnected services. Okay. So, what our aim is to effectively design a threshold function that can depend upon some prior knowledge of the crossover RS, and what else? It can be the communication pattern of the mobile terminal, how frequently it is communicating, or the type of service it desires to take. Okay. Even the tolerable level of the mobile terminal itself, the knowledge of all these parameters are very essential to design a threshold function. Now, next is RSS with hysteresis. Hysteresis is a kind of margin in which it allows the handoff to take place only when the base station, that is the new base station, becomes quite stronger than the current base station, this base station that is currently serving the user by some hysteresis margin h. Okay. So, what this allows, the mobile terminals can now drift even farther into the adjacent cell boundaries. So, when it goes deeper into the coverage of another base station services, then there is a very less chance of getting our calls disconnected or even disrupted. Okay. Disruption is like a small period of time. The call will not get disconnected, but there will be some disturbances, some noise or some technical glitch during our conversation. Okay. And disconnection is like complete stopping the services. Okay. You have to redial again to get the service. So, there will be no call disconnection or disruption in this case, because our mobile device is going quite farther into the coverage of another base station. Okay. So, it's like it would now guarantee even more quality of service, a guarantee towards that the signal level will not fluctuate. So, what is happening? We are completely getting prevented from the problem that was created earlier by ping pong effect. Okay. So, in this case, in the diagram you can see that the base station 2 is given a margin h. Okay. And now the junction, the intersection of the two RSS levels are at B, at point B, and it is quite far away from the point A. Okay, this point is the one where ping pong effect tends to happen very frequently. Okay, so this method, no doubt, is comparatively it will act better than the threshold version of RSS and the normal version of RSS as well. Now let's move ahead. We have a method that is even more better with its existing counterparts. Now we have RSS with hysteresis and the threshold. That is, we are combining the goodness of both the methods. So very simply, now the mobile station will hand off only when it sees that the target base station, whichever base station it's towards, whichever base station it is moving, whatever its progressive direction is, if that base station is stronger enough than its host base station by some margin h, and also it is not violating a particular threshold, okay, so it becomes easier for the mobile station now to effectively decide which is the optimal point for handoff. And then of course we have some prediction techniques. Now whatever techniques so far we have just spoke about, the hysteresis and threshold alone, and the normal version of RSS, these all are the dynamic methods. The methods that on the fly decide whether the mobile should hand off or not. They are in charge of deciding at what point of time or at what level of RSS or at what particular position with respect to distance a handoff should take place, or it could take place in future. Okay. Now prediction techniques are somewhat they are non-dynamic one, because here wherever prediction is there, what we are doing some research on the background, and we are trying to build some model on the basis of which we can do kind of predictions that given a particular area, what are the tendencies of getting handoffs, what are the tendencies of the users to communicate with each other, what type of service they want to acquire, etc. Okay, so there can be a lot of prediction algorithms, and it can be helpful to us for estimating the rate of decrease in the RSS of the mobile terminal, and also to predict what will be the optimized value of threshold as well as hysteresis given a particular region or a particular type of user, that is users intending for a particular type or level of services. Okay. Now together this will help for minimizing the number of handoffs. Obviously the handoffs will get minimized a lot, thereby increasing the services being imparted by that particular network, and it will assess the optimal location for the occurrences of handoff on the basis of prior information of the other mobile devices in that location at some hour of a day, etc. It can assess, it can make estimation of what are the optimal locations, the possible locations where chances of handoff tends to be high and where it tends to be low likewise. And it maximizes quality of service overall. Also it improves the system capacity even in non-uniform traffic scenarios. System capacity means it has now the capability of supporting more and more number of users, and since the users will get satisfied with the quality of service and all, they tend to get associated with that particular network, which is good for obviously the network administrators and the designers. Even in non-uniform traffic scenario means that there are certain traffic scenarios where the frequency of service sharing or whatever multimedia content sharing might not be high. So in given a particular location, even in a region of interest, there are different sections, different sectors where the traffic is too low or too high. Okay, so the traffic pattern is also important, and this type of prediction technique can be useful to do a kind of research on the pattern of traffic and apply the dynamic or non-dynamic techniques accordingly. Now we come to quality of service. It is a very core challenge in multimedia networking, especially when we talk of the multimedia sharing of content over the web. When we are talking about the web, it means that we are talking about the wireless channel, and wireless channel has a lot of impediments associated with it. As we know, there are chances of noise, chances of different impairments like from the interference issues like co-channel interference or just channel interferences. Even there are other parameters, phenomena like reflection, refraction, scattering, and that is how a signal can get diffracted or any other kind of impediments. Okay. So here, when associated with multimedia, quality of service becomes very important issue to be dealt with. Now, quality of service is basically important for supporting audio-video streaming of data. As unlike the text data can easily get buffered. We don't need very complicated storage or transmission policies for loading the text data, but when it comes on multimedia data, it's a superset. It contains, along with the text data, it contains audio, video clips, animation, so many things into one package that it will take more time and complicated technology to get associated, so that the end user can experience the richness of the multimedia. Okay. So obviously the quality of service has to be maintained, and why it has to be maintained? Because of the wireless domain is there in our picture, and whenever wireless domain is there, there will be chances of frequent topological changes. Okay. Now the topological changes can be there due to several reasons. First, it can be due to user mobility. The users are mobile. The users are holding these multimedia handheld devices, so obviously they are not going to be stationed at one position. Maybe the rate of mobility is different. Maybe they are walking or on bicycle or cars or even trains, etc. Okay, so there are different rates of mobility. So user mobility is one. The second is the entire mobile platform is on motion. Okay. What else? The availability of base towers. Now in base towers, what happens? Often we have seen that whenever there are weak signals or there are non-availability of the towers, our services goes down. Our expectation regarding a particular network service, it goes down. So availability of base towers are very important, because whenever the towers goes down, the entire region associated with the network will get dead. As a result, the topology will change. The topology that initially was started with may look different with time and services. Next is highly variable network traffic. Now, whenever the network traffic of multimedia users are there is a chances that the traffic rate will be very bursty. It won't be uniform. It will be very bursty, very non-uniform over space and time, both domains. And since wireless channel, so it tends to be very noisy. There can be distortion in the signals. As a result, whenever the distortion crosses a limit, then entirely the packet gets lost. And whenever a packet gets lost in the communication, because the communication consists of so many packets chained into one, whenever one gets distorted, it means that the whole communication goes down. So again, our device is there, it has full tower or battery power, everything, etc. But due to over noisy channels, the distortion level has gone beyond, say, some threshold that has been set, predefined in the system. There can be problems, okay, and these problems can lead to certain topological changes. Next, the limited bandwidth. Yes, bandwidth is very limited. so we have to make proper use of it. If you are not using it, as we have studied before, with the help of guard channels and all, doing some kind of special treatments to the prioritized or non-prioritized users, etc. In that case also our topology is going to hamper. Okay. Next, sharing of resources, levels of prioritized users are equally important. And hardware technology is the devices that supports multimedia services has to be of quite upgraded one. Along with the hardware, the software support should also be considered, because what happens that we have tower, we have proper coverage, we have everything, but there might be hardware and software incompatibility, because of which video or audio, that is a multimedia content, fails to stream on our mobile devices, and we feel disconnected from the network. So these are the things that should be kept in mind to consider for what type of quality of service should be designed, or what type of quality of service is deserved for particular levels of the users. Welcome back, viewers. Now, we were speaking about the quality of service, its significance, more importantly for audio and video streaming. Now, how this audio video streaming is important? So its significance can be checked on how its impact is there on the media, on the online media. So there are different streaming media available online. The first is chat applications that we are all very aware of. Previously in chat applications, people used to use only text, but these days you can share presentations or even whole some video clips, audio clips, or some 3D animation. If you want to share, you can do it. Even certain reports can be sent with rich multimedia graphics, etc. So nowadays video conferences and these desktop sharing applications, etc., everything can be shared, and they can be done over chat applications, chat platforms. Okay, so this is very important, because whenever we are sending such rich multimedia on the web, it means that we need our data to be streamed on the other end. Then viral video. These days people are very much into doing things like tweets and retweets or likes, sharing a particular link, embedded link can be shared with some friends or etc. And these friends can be there on Twitter or whatever, Facebook. So whenever you are sharing the link, it means the embedded multimedia services are there. Okay, so again their streaming is important. Then video archives. Yes, previously there used to be blogs, but these days you have video blogs. So everything whatever you want to write, you want to let the world know, you are doing it with the help of video clips, uploading the video clips. Again, whenever video clips are there, you need proper streaming of those as well. Okay, there are commercials, they can be used for commercials purpose as well. Then video clips of news recaps, etc. Then we have internet channels. These days most of the lectures, etc., are uploaded in form of videos, so that the students can listen to them online as well as download them depending upon the streaming speed, obviously. So the video archives and internet channels, they are these days very much into trend. Then we have online video gaming portals are there, action games, even puzzles, memory games, etc. are there. And obviously e-learning environments that are based on training and learning, interactive teaching methodologies, etc. And obviously e-commerce applications that are coming up these days, as in most of the shopping portals online that are available, they offer e-dressing rooms or virtual dressing rooms. What happens here is whenever user passes by through this type of services and checks out for some maybe some clothes or whatever, they can give their own measurement, and according to that the site intelligently shows that actually how a person can look like when that particular dress or whatever material is worn on. So it's a very smart way of providing multimedia to the users. Then there are 3D product views. You want to buy something, some electronic item or something, or any other item, and you want to have a 3D rotation of how that item looks like at any angle. This also again calls for streaming multimedia services. So we understand that streaming media is so much into these days, and that is, it is in the trend, as well as it has become a pervasive, it has become so much embedded into our life that we are using it in our daily basis. So for making the streaming media possible, quality of service in multimedia services has to be maintained. Now, very strictly speaking, multimedia services, they offer a quality of service on two levels. The first is connection level and the second is application level. When we are talking about the connection level services, it means that we want our call to get connected, and once connected, it should be continued as well. It's not that it got connected and we were able to speak only a minute or two and then it got disconnected. No, it should get continued throughout. Okay, so to measure the connectivity and continuity, we have two parameters with us. The new call blocking probability and handoff dropping probability. These are the two parameters, measuring parameters. And what this new call blocking probability is, this is a probability for restricting the new calls to enter into the system. That is, they cannot enter the system. What is the probability that they cannot enter into the system? That is, they cannot take up the network services. And this might happen because the call is not supported due to several reasons. Often we have we have heard on the phones that the channel is busy, try after some time, or there can be no towers at all on our mobile systems, or even we are maybe because out of the coverage area of the nearby base stations. So our request gets rejected due to unavailability of certain network resources. Okay. Now, the handoff dropping probability is what? This is the probability that forcefully terminates, with what possibility ongoing call gets forcefully terminated, right? Now, whenever user moves from one cell to another, its call gets handed over to the next potential station. Now, if this next station, the new station, is not having enough resources to support the ongoing call, then the call will simply get dropped. Or even if whatever its coverage area gets fluctuated due to some reason, say noisy channel or whatever, interferences, etc. In that case also, the handoff dropping probability shoots up. Okay. Now, what is a major concern here is dropping the ongoing call can be preferred than blocking the new calls, because if my call never gets to enter the system, we won't have much faith in that particular network, right? But if very less often my ongoing call gets disconnected, then it's like perfectly okay with us. We can obviously redial again and get the service. So it's very important for the new calls to enter into the system. That is, the new call blocking probability, it should be less, so that more and more calls gets into the system, and the handoff dropping probability can be taken into consideration to be like, it can be low or whatever, it can be adjusted according to the network needs and the user requirements. Now, the application level quality of service. Now say our call is continued, it was connected and our ongoing call was carried out without any disturbances, without any noises, etc. Okay. Now we are concerned for such a call that is connected and continued, what are the different parameters that specifies its performance. It can be the delay, the jitter, any packet error, or some loss performance. If there is much loss in the frames, then what type of performance it's going to give, etc. The system throughput, even the buffer size and queuing mechanism is again a very important parameter that plays to define the quality of service at application level, because the new calls that gets into the system, it is up to the efficiency of the queuing mechanism that how these calls, that is these new requests have to be handled. Sometimes it can happen that ongoing call is very important, so we have to prioritize the ongoing calls such that maybe some number of tolerable new calls get lost, but at least that particular ongoing call that may have some national importance or of defense importance, etc., should get continued through. And again, one more important is audio and video synchronization. We have often seen some movies or some videos that we are able to see the video properly, we are able to hear the audio also, but with the lip movements, maybe the audio is not properly synchronized. So for continued connected and continued services, it is important that all the services are synchronized. There can be other supported services like the subtitles. Maybe the subtitles are coming late and the video and audio are synchronized. So this can be other aspects. And how to ensure this application level QoS? As you can see that it can be done by packet access probability, then scheduling schemes, where the different scheduling schemes to schedule the packets so that they can properly reach the destined location without loss or collision, etc. Then packet routing methods. Obviously, these are the routing methods that will help in successful delivery of the multimedia content at correct time and location. Then channel encoding schemes to ensure tolerable loss in performance, and obviously the levels of power control. Now, there are different channel improvement schemes that are available with us. Now, why the administrators would like to improve the quality of the channel when the channel, say whatever we are experiencing, it's like good, the services are good, everything is fine, then what are the requirements that channel capacity needs to be improved? It is because day to day there is a upgradation in the technology, so user wants to acquire more and more upgraded the feel of upgraded technology. So they might require better services, okay, or it can happen that more and more users are coming and joining a particular network. So what about the increase in the number of users per region of interest, that is per cell. So we know that a cell is of limited size and the users can come unlimited at say a particular time of day or on a particular within a particular region, etc. So how to handle such issues? So it becomes very important for the administrators who are owning the network, who are managing the network, to time increase the channel capacities. Now this can be again due to increase in service demand, as we have just discussed on, or it can be due to non-uniform traffic pattern. Whenever we are speaking about traffic pattern over time, it means that they are hotspot areas, hotspot durations. At some point of day, the communication on the internet can be very high. At some point of day, it might not be so. Okay, likewise. Then we can have several levels of service preferences, etc. Now, what are the common techniques to increase this channel capacity? The first one, very general way, is to control the power of the transceivers that are implanted in our mobile handheld devices. Okay. Others are like the cells can be splitted or sectored, or microcell zoning can be applied, etc. So if we consider the power control, what actually we are doing is we are sectioning the transmission power into different levels. That we know for a particular transceiver, what happens, there is a level 0, that is the least amount of power with which that transceiver can stay alive. Okay. And the maximum signal strength, the maximum relative signal strength beyond which it cannot reach. Okay. So between this level 0 and say some level n, there can be several levels into which the transmission can be broken down, and there has to be some flexibility that according to the quality of service requirements or any other challenges that comes, according to them, this level can be set by the device. Okay. And obviously level 0 means it's temporarily almost turned off its radio, but obviously it's not dead. It should have such remaining power that can help it to trigger its circuitry whenever required. And obviously scheduling the duty cycles is very important. Duty cycles means the multimedia devices or any electronic device, they operate between very like it's very roughly speaking between two states, the active and the dormant state. Okay. So there should be some mechanism so that the toggling between the active and the sleeping state or the dormant state can be done transparent in a very transparent manner. Now, on the basis of a type of category, we can have two different power control mechanisms. The first being low network workload, that is particularly for those networks where the workload means the communication load is not very high, it's quite low. So for that type of networks, what happens, most of the mobile terminals, they tend to remain in the idle state. They are not transmitting and they cannot obviously completely turn off their radio. So they are in their idle state, and whatever energy is getting lost, it is not due to transmission or communication or whatever reception activities, it is only due to the idle state. Okay. So energy consumption is very little, and the transmission requirement for communication is also very rare. So we can say that communication is a very rare event here. In that case, what happens, whenever a mobile device will have some packets to transmit, rather than going via other devices, what it can do is it will extend its power using the power level phenomena. It can extend to say level n or level n minus 1 and reach its intended destination, and then again return back to idle or sleep state. Okay. So what are the advantages that we get from here? As in the figure, we can see that if we are going from the sender to receiver via node A and B, we are unnecessarily waking up those nodes. Those nodes have nothing to do, right? So no need for waking up unnecessarily the radios of other devices. So the sender can take a direct path by enhancing its radio, by enhancing its power level, and reach the receiver. And we can see that there are no direct connections previously between sender and receiver. The connection it builds on the fly between the sender and receiver, and once the transmission is done, there is a power that is invested in the direct hop. When the transmission is done, then the sender will again go back to whatever level it was before. For high network workload, there is a different strategy. Here what happens, the packet transmission among the sensors or the embedded within the transceivers, the circuitry of the multimedia devices is quite frequent. Here the communication is very frequent. So when the communication is frequent, we cannot every time require our sender electronics to just go to level n, the highest power level, and deliver your packet to the particular destination. That way there will be severe loss of energy because the communication rate is high. We have to repeat that particular operation over and over again. So why not go through other way, taking the small hops and reaching to the destination. Okay, so this will call for balanced power usage over the multiple hops, and this will also call for since shorter hops are now used, so the power level required for transmitting packet from the sender to as in this diagram to location A, and from location A to B, from B to the receiver end is quite less. Okay, quite less as compared to the previous case as with the low network workload. Okay, and but what will happen here, the delay will increase. The delay will tend to increase a little more because it's going through 3 paths, like it's not a direct path. Now the path is broken down into 3 sub paths. So obviously delay incurred is more, but transmission power used is less. Okay, so since a longer path is used, obviously in some way we can say the reliability is also increased, because when the sender is sending its packet as in the figure to the multimedia device A, then there is some routing facility, some buffering facility available with that router. It will store it. So even while forwarding the same packet to location B, if there is some kind of network loss, then the previous copy is always there with A. So that way reliability increases, and these are important for networks having higher workload. Now the other techniques apart from power control is cell splitting. Now here the diagram, very interestingly, it shows that the cells that previously we have seen this cellular architecture. Okay, now we can see that here the cells originally, what was the size of the cell, the homogeneous cells with say radius r. Now that r parameter has gone, it's diminished a lot, and it has formed subcells within a particular cell boundary. So now our macro cells, if we are calling our cells as macro cells, they are getting reduced to micro cells and pico cells. Okay, and according to the architecture supported by cell splitting, each of this subdivided cells will have a separate base station. Okay, and such stations will have reduced antenna height. And whenever the height of the antenna gets reduced, mind it, the coverage will also be reduced. Okay, the height gets reduced, the coverage area that it spans over will also get reduced. And as a result, since we are dealing with now a very small area, the relative signal strength imparted by that particular base station in that area will be high. Okay, and obviously number of cells are getting increased, as apparently it can be seen in the diagram. So more and more number of users will get supported, and there will be reduced transmission power because the users are very close to the base station, because the same phenomena, area decreases, now the reachability of the users to the base station will be, the distance will be quite relatively shorter, and more users will get supported. Okay, so what we can see here is cell splitting will not disturb the initial channel allocation. We are not asking the bandwidth, the network administrators to provide us extra bandwidth. If we are our cellular architecture is based on, say, the standard n equal to 7. Remember, n is the number of cells in cellular architecture, so it can go with the 7 frequency bands. Okay, they don't need additional frequency bands. So initial channel allocation stays. And what else? Spectrum usage or extra bandwidth requirement is not there. Okay. But what are the limitations that are associated? Limitations are also there. The first is, since the number of cells have become smaller in size, so they have obviously become larger in number. So if they are larger in number and smaller in size, it calls for more frequent handoff. If the mobile objects are in motion, even in low level motion, still there is a chance, there is a fair chance that handoff will take place, because now cells are nearby to each other. And then what happens? The channel assignment to micro and pico cells should also be done, and it becomes it gives an additional overhead to the system, and it becomes therefore a very complicated task to manage. And obviously the hardware installation cost, it shoots up, because now we have more number of cells, and each number of cells are having their separate base stations. To launch base station in each of the cell is a tedious and obviously time consuming and resource consuming task. So from this diagram we can get a good idea of what a macro cell looks like, a pico cell and micro cell looks like. We can see that as we move from macro cells to micro cells, the bit rate increases to 1 Mbps. Previously it's generally 0.3, so it shoots up to 1 Mbps. What else? The delay will get reduced. Previously it was in ms, now it is in ns. Okay, ns, that is nanoseconds. So delay is very less because the area is small. And the fading in microcells that are smaller in size will now use Ricean distribution, as we have discussed earlier, that whenever there is a clear line of sight communication, Ricean distribution is rather used for controlling, for predicting the extent to which the signals may fade. And the transmission power, obviously the distances have got reduced, so transmission power required will be lesser comparatively. And this is all because the radius of the cell, of the original cell, that is the macro cell, is reduced drastically. Now cell sectoring. Cell sectoring is what? Here in this approach, the rather than dividing the actual scenario into smaller cells in pico and micro cells, why not sector it to have better results? In sectoring, each sector will consist of separate antenna. Mind it, they are not base stations now. No separate base stations are given. Base station is only one for that particular cell. But since we are dividing the cell into sectors, now the sectors will have different antennas. And these sectoring angles could determine the number of sectors in each cell. There can be homogeneous or heterogeneous sectoring, depending upon the type of antenna services and hardware platforms that are being imparted in those cells. And as in the figure, we can see that different sectorings are possible with the help of different angles. A 120-degree angle can give you 3 sectors. Similarly, 90-degree can gives you will be giving you 4 sectors. And with 60-degree we can get 6 sectors. Okay. And obviously whenever a moving object, a mobile multimedia object passes or crosses the sectors, between sectors, then there will be handoff, but these handoffs are they require nominal impacts. They don't use much of the network management, they don't interfere much of the network management issues. So many modern day base stations are there that support sectoring related handoffs. And what are the limitations we have here is sectorization results in reduced channel reuse ratio. Now the channel reuse ratio is hampered, which was previously not disturbed in case of cell splitting. Now it gets hampered, it gets reduced, and we know that whenever the channel reuse ratio is reduced, it means that what we are doing, we are playing with the co-channel thing. that is whenever we are using same frequency in the channels that are not say within a particular distance, it means that it can call for interference, okay, thereby imparting noise and distortions in the signal, right. So, what is the solution? The solution is we can reduce the number of cells per cluster, or we can use directional antennas. So, using directional antennas means sector can use frequency band that is entirely different than the other bands in that particular channel reuse ratio. Just to summarize, we can see that the cell splitting, in cell splitting what happens, the parent frequency is subdivided into micro and pico cell frequencies, but in sectoring, each cell is having the entire set of frequency band. The channel reuse ratio is not disturbed in cell splitting, which is a very advantageous point, but the radius gets reduced, and since radius gets reduced, so we are having micro and pico cells obviously. But in cell sectoring what happens, we are not disturbing the radius of the hexagonal cells, but rather we are reducing the channel reuse ratio, okay. Then what, there are many base stations in cell splitting technique, but only a single base station per cell is available with sectoring, okay. And to make it feasible, we are using many directional antennas, while in case of splitting, in cell splitting, the base station will comprise of a single omnidirectional antenna, that is the antenna that radiates equal the signals of equal strength in all directions uniformly. And what else? Obviously there is no overlap, which is common in both the cases, the cell splitting and sectoring techniques, and the handoffs between the cells will occur. Here the sectors will occur in cell sectoring, and the handoff decisions will be made by the base station in case of the cell splitting, while directional transceivers that are there with the sectors in case of cell sectoring will be doing the handoff decision and management issues. Thank you.
We would like to thank Dr. Advaita Sinha for giving us a very, very productive session. Dear friends, we believe that if you have liked the lecture, then if you could share your feedback with us, then it would be beneficial for us to give you the maximum through our lectures. So dear friends, give your feedback as well as if any kind of question which you would like to be answered at info.cec@nic.in. We would be uploading this lecture on YouTube very soon, so keep watching us and keep writing us. We would be meeting again. Till then, take care. Goodbye. Thank you, ma'am. Thank you so very much.
Thank you.